Now let's come back to our flowchart or algorithm. What we are going to do, we are deploying two 64-bit register, RM and D, which is reminder, and divisor 64, which is 64-bit divisor, and then loading the dividend into the reminder register to the lower half and divisor bit pattern to the upper half of the 64-bit divisor register. Then we subtract remainder with the divisor 64, that bit pattern. If it is a negative, if it is a negative, then we do what? We do a rollback. We do just a reverse operation, remainder equal to remainder plus the divisor 64, and simply left shift the quotient bit. Okay, so quotient bit, let's say we of course we need to initialize with zeros, all zeros. That's the assumption. So we simply left shift the quotient bit. Now, if the remainder is not less than 0, means it's a 0 or positive, then we insert 1. So we left shift the quotient and or with 1. So that will insert a 1 into my LSB position of the quotient. And of course, next step is to right shift the divisor 64-bit register one position to the right. Okay, this is a right shift. And we do this 33 times. Okay, remember, like 8-bit we needed to do 9 iteration. For 32-bit we need to do 33 iteration to finalize my quotient value. Well, so with this application, we can well imagine we need to have two 64-bit register with shift capability, both of them, right? Because not both of them actually. We are not shifting remainder register. It's just an addition subtraction. Just load is fine. Only divisor 64 need to have a right shift capability, and we need to have a multiplexer to go into either direction, right? But that multiplexer will now be inside your control and test. Okay, so there is some decision making element there to go either way. It is it's basically not determining which data you pick up. It's basically determining what operation, whether you want to do a rollback or not. That's where the decision making is coming in this algorithm. Okay, so we have that 64-bit divisor register. We have the remainder register loaded with the dividend 64-bit. We have adder subtractor 64-bit. Mainly it is subtraction, then rollback it is addition. So we need to have both adder subtractor circuit deployed. Dividend only need, and remainder register only need a write operation or load operation, where divisor 64-bit register needs a shift right operation. Quotient, we are looking for a shift left capability with all loaded with zeros to initialize form, and then this little part is just, I want to make it a digital circuit to make sure you understand the whole process. So this little circuit is determining whether I am inserting a 1 into this quotient register, the LSB position, or inserting a 0. So if in this case, by checking the result of the remainder register, if it is a negative, then it will send out a signal 0 onto load on Z, this control signal, so that AND would be a 0, and it will come with this 0, insert 0 in the quotient bit. Now, if it is become a positive, then it will issue a 1 into this load on Z, and outcome of the AND would be directly onto the quotient will come to the 1. 1 bit will be inserted into the quotient register. So you can also say that instead of having this data path element, we could directly feed this load on Z into this quotient, because if it is a 0, we want to insert 0. If it is a 1, we want to insert 1. So we could have feed that quotient bit directly. But I want to show you that we have some control signal controlling a data path module into the whole circuit. So this controller will now run your entire algorithm or flowchart as we have seen in the last slide and iterate through these steps for 33 times. Okay, and it will control this divisor register at the appropriate time to shift right, quotient to shift left, insert 1 or zeros, load the result into the remainder registers, and so on and so forth. And then at the end of the day, after 33 repetition, it will raise the flag that, okay, I'm done. You can pick up the result. The quotient register will hold the quotient, and your remainder lower half will have that 32-bit remainder, not the upper half. Okay, so that's the whole strategy.